Acid-base properties of salt solutions. Hydrolysis. Water molecules ionize to form hydrogen ion and hydroxide ion. And this process only proceeds at a very small percent. For example, in pure water, the concentration of hydrogen ion and hydroxide ion are both 10 to the minus 7, and that's a very small number. The product of these two ions is 10 to the minus 14. Okay, this is called ion product of water. It's a constant that applies to even a non-pure water. For example, in a non-pure water, hydrogen ion, hydroxide ion may be different. Suppose we have hydrogen ion 10 to the minus 2. Then the hydroxide ion must be 10 to the minus 12 because the product is 10 to the minus 14. Okay, now 10 to the minus 2 means 0.01, and 10 to the minus 12 means 0.00. You have 12 zeros and then 1. So this is a very small number. So 10 to the minus 2 is greater than 10 to the minus 12. So in this non-pure water solution, we have more proton or hydrogen ion than hydroxide ion. And this is called acid solution. So in acid solution, we have more hydrogen ion than hydroxide ion. Okay. On the other hand, if it's a basic solution, we have more hydroxide ion than hydrogen ion, but the product of these two concentrations always 10 to the minus 14, the ion product of water. Because it's inconvenient to write so many zeros, we define pH value is negative log of hydrogen concentration. So in this solution, because we have 0.001 or 10 to the minus 2 hydrogen ion, the log is just 2. So the pH in this case is 2. Okay. And so here is a pH scale. All right. For pure water, because the hydrogen ion is 10 to the minus 7, so negative log 10 to the minus 7 give you 7. So in pure water or neutral water, pH is 7. In acid solution, you have more proton. So the pH is smaller than 7. In this case, is 2. Okay, so the smaller the pH, the more acidic the solution is. On the other hand, if you have a solution, let's say you have more hydroxide ion. So let's say hydroxide is 10 to the minus 3. Then the hydrogen minus 10 must be 10 to the minus 11. Okay, that's a very small number. So the pH in this case is 11. So when pH is 11, then the hydrogen ion is a small number, 10 to the minus 11, and hydroxide is 10 to the minus 3. So you have more hydroxide than hydrogen. There are several theories about acid-base properties. Okay, and the simplest one is called Arrhenius model. In Arrhenius model, acid is defined as the compound that produces hydrogen ion. Okay, in aqueous solution, as we shown above, if a compound produces more hydrogen ion in the solution, then because the product of hydrogen hydroxide ion is always 10 to the minus 14, so you have high hydrogen ion, you have less hydroxide ion. The pH is less than 7. All right. Here is a list of strong acid. Nitric acid, HNO3. Okay. Sulfuric acid, H2SO4. Hydrogen chloride, hydrogen bromide. Okay. So it's very useful if you can memorize some strong acid. Okay, later it is very useful if you have some strong acid in mind. Okay, you will see that. So remember, nitric acid, HNO3, sulfuric acid, H2SO4, hydrogen chloride, hydrogen bromide, these are strong acid. So if you see something else, then they may not be strong acid, they will be weak acid. Okay. Similarly, the base, okay, in Arrhenius model is the one that produces hydroxide ion. So that's hydroxide ion. All right. So if a compound produces hydroxide ion, then the solution has more hydroxide ion, and then you have less hydrogen. The pH will be more than 7. Okay, that's the basic solution. So here is a list of strong base. All right, sodium hydroxide. All right, so group number 1, okay, metals, for example, lithium hydroxide, sodium hydroxide, potassium hydroxide, rubidium, cesium hydroxide. These are all strong base. Second group, calcium, strontium, barium hydroxide. So for example, barium hydroxide. Okay, because the second group, so you have 2 plus, you need 2 hydroxide. So these are strong base. So remember these, they are strong base. And therefore, if you see something else, for example, if you see zinc hydroxide, it's not in the list, so it's a weak base. All right, so remember this list of strong base. All right, strong acid, strong base. And these are under the definition of Arrhenius model. Now, there's other models, for example, Bronsted-Lowry model. In this model, acid definition is similar to Arrhenius, that they produce proton. Okay, so acid is the same. So if you see hydrogen chloride, all right, that's belongs to Arrhenius acid because it produces hydrogen ion. It also belongs to Bronsted-Lowry model because it donates proton. It has a proton that can donate. All right, so acid, all right, belongs to Arrhenius, also Bronsted-Lowry. They are the same, but the base definition are slightly different. In Bronsted-Lowry model, base is defined as a proton acceptor. Okay, so let's look at Arrhenius base. So sodium hydroxide, this is a Arrhenius base because it can produce hydroxide and sodium, right? So this is hydroxide. So that's Arrhenius base, but it's also Bronsted-Lowry base because it can react with hydrogen. The hydroxide react, react with hydrogen to form water. And because hydroxide react with hydrogen, so it is a proton acceptor. As long as it can react with hydrogen ion or proton, then this is a Bronsted-Lowry base. So all Arrhenius base they also belongs to Bronsted-Lowry base, but Bronsted-Lowry base is wider. For example, ammonia. Okay, now ammonia is not Arrhenius base because it doesn't provide hydroxide, but it can react with proton. So it's a proton acceptor. And therefore, ammonia is a Bronsted-Lowry base, but not Arrhenius model. So Bronsted-Lowry model covers all the Arrhenius model, but it has more, it's wider, okay? When a strong acid and a strong base react, hydrogen ion flow strong acid combine with hydroxide from strong base to form water molecule, and the rest is called salt. A salt is a chemical compound consisting of an assembly of cation, here is sodium ion, from the base, and an anion, here is a chloride ion, from acid. Okay, so salt, cation, anion comes from acid and base. Now the reaction can also be written as ionic reaction. So because we have a strong acid is also called strong electrolyte, which means it completely ionizes to the two ions, hydrogen ion, hydroxide, or chloride ion. Okay, remember this only happens to strong acid. Similarly, sodium hydroxide is a strong base. Strong base is a strong electrolyte, is completely ionized to sodium ion, hydroxide ion. Okay, so now you see the importance of memorizing the list of strong acid, strong base, because when you see strong acid, you can write as two ions, cation and anion. Strong base similarly. Now, for example, if you have a weak base, all right, so let's say zinc hydroxide, all right, in ionic reaction, you cannot write zinc and hydroxide because it only goes very small extent. Mostly are still the weak base, the zinc hydroxide. Okay, very small extent goes to ion. So when you write ionic reaction, you should write the molecule. All right. So when you combine all these ions together, only these two react. It's hydroxide and hydrogen forms water. Sodium is still there in the reactants, in the product, they are the same. Chloride ion, same, remains the same, and these are called spectator ion. They don't change between reactants and the product. So the net ionic reaction is hydrogen ion, hydroxide ion forms water. So this is the net ionic reaction. That's what happened when you combine strong acid, strong base. Okay, the chloride, sodium, they don't change. All right, so after you form water, the rest becomes a salt. So these two combines, that's the salt, but it doesn't change before and after the reaction. So if you have a salt, sodium chloride, all right, when you dissolve in water, it will ionize to sodium ion, chloride ion, and they don't react with water, so it doesn't affect the pH value. So cations, anions of strong acid, strong base. So in this case, sodium chloride. All right, sodium comes from strong base, chloride comes from strong acid. This kind of salt have no direct effect on solution pH because they are spectator ions. Okay, they don't react with water, they don't change the pH value. So the conclusion is a salt made from strong acid and strong base is neutral. Okay, water is not affected. It's just pure water. It's like pure water. It's a neutral solution. Okay, another example, let's say lithium sulfate, for example. Okay, so remember lithium is a group 1 cation, so this comes from lithium hydroxide. That's a strong base. And the sulfate, remember the list of strong acid, sulfuric acid. So this comes from sulfuric acid. When these two combine, hydroxide, hydrogen forms water, and the rest is lithium sulfate. So this salt comes from strong acid, strong base. And the lithium and the sulfate, they are spectator ions. They don't affect pH value. So this salt in solution is neutral. in this acid-base reaction, you should recognize that sodium hydroxide is a strong base, but nitrous acid is not a strong acid. It's not in the list that we see before. Okay, we have nitric acid. So this is a strong acid, but this is not. All right. So when we write ionic reaction, a weak acid you cannot separate into ions. So you should write HNO2, but the base is a strong base. So you write as sodium ion hydroxide ion. And when you combine these two together, hydroxide ion take this proton away from this weak acid, forms water, and the rest is the salt, sodium nitrite salt. Okay. Now compare with the strong acid, strong base reaction. And here we only have one spectator ion, that's the sodium. So sodium is the spectator ion because before reaction, the strong base ionized to sodium ion. After the reaction, the sodium ion is still there. Okay, and nitride ion is produced in the product, but not in the reactants, because in the reactants we have a weak acid. All right, after the proton is taken away by hydroxide, it forms this one. So this is not a spectator ion, and therefore when we write ionic reaction, only sodium is removed. So the ionic reaction is nitrous acid plus hydroxide forms nitride ion and water. Okay, so that's the difference between the strong acid, strong base reaction and the weak acid, strong base reaction. You only have one spectator ion, and that's the sodium comes from strong base. The anion from weak acid is not a spectator ion. And also notice that when we write strong acid, strong base reaction, for example, sodium hydroxide HCl forms water plus sodium chloride. Here you only have one arrow. So the reactants completely forms product. But in this case, we draw two arrows, means that the product also go back. So the reason is this is not a spectator ion. In the reactants product, they are different. So if you have here in the product, it can combine with water, forms this weak electrolyte or weak base or acid, sorry. So nitride ion plus water can go back to the original weak acid. And this reaction, the back reaction is called hydrolysis. Okay, hydrolysis is the anion from weak acid. So that's the anion from weak acid hydrolyzed back to the weak electrolyte, forming, okay, when this goes back, it forms the weak acid plus extra hydroxide. And hydroxide, so increase concentration of hydroxide and make the solution basic. So the interesting thing here is if you have a salt, sodium nitrate, okay, it's a salt. When you dissolve in water, it ionizes to sodium ion and nitrite ion. And sodium ion is a spectator ion. It comes from strong base, so it doesn't react with water. But nitrite ion come from weak acid, hydrolyze, okay, with water, hydrolyze to go back to the weak acid, generate extra hydroxide, and that gives the solution basic. So a salt solution can be basic, not necessarily neutral, as we shown in the last slide. If the salt, for example, sodium chloride, both come from strong acid and strong base. They both are spectator ion. They do not participate in reaction, so the sodium chloride does not affect pH value. It's neutral. But sodium nitrite, all right, this salt is basic because sodium comes from strong base. It's a spectator ion. Nitrite is not. Okay, so how do you memorize it? Okay, so here is one way to remember it. If a salt comes from a strong base, this is a strong base, but a weak acid, the stronger one wins the solution. So strong base wins the solution compared to weak acid, and that makes solution basic because you come from strong base, so the solution is basic. But the real reason is the nitride ion come from weak acid hydrolyze back to the weak acid, generate hydroxide, and that makes the solution basic. So the conclusion, all right, here is important conclusion, and that is a salt made from a weak acid, all right, so weak acid, that's a nitride, and a strong base, sodium, so again, sodium nitride, all right, and sodium is strong base, comes from strong base, nitride comes from strong weak acid, is basic, the solution is basic, and you have more hydroxide, pH is greater than 7. So here are some examples. Okay, we already see sodium nitride. This is potassium, acetate. So potassium acetate. All right. So how? What are these ions? Where do these ions come from? So potassium comes from potassium hydroxide. That's a strong base. And what about acetate? Acetate comes from a weak acid, HC2HO2. That's a weak acid. So how do you know it's weak acid? Because it's not in the list of strong acid. So it's a weak acid. And therefore, remember, the stronger win. So here's strong base. So the solution must be a base. So this is a basic because it comes from strong base, a weak acid. All right. The real reason is this: the acetate hydrolyze, go back to the weak acid. Okay, so C2H3O, and because water, one hydrogen is taken away to form weak acid, so you have extra hydroxide, and so that makes solution basic. Okay, all right. So remember, a salt, if it comes from strong base but weak acid, the solution is basic. Now similarly, okay, we are not going details, but here, if a salt comes from a strong acid, a weak base, okay, remember stronger one wins. So strong acid wins, so the solution is acidic, and this solution is acidic. Examples are, okay, ammonium bromide, so zinc chloride. So let's take this as an example. So zinc comes from zinc chloride or hydroxide. As we know, it's a weak base, and chloride comes from hydrogen chloride, and that's a strong acid. So strong acid wins, the solution is acidic. Okay, now what is the real reason for the solution to be acidic? It's because the chloride comes from strong acid, so it's a spectator ion. It doesn't react with water. But the zinc comes from a weak base, so it will hydrolyze back. So it reacts with water and goes to this one. Because it takes hydroxide from water, so you have hydrogen ion left. You generate extra hydrogen ion and make the solution acidic. Simple questions. In this table, the first column shows solution of salts, and the second column asks you if there's any ion expected to hydrolyze. And the third one asks you if there's any spectator ions. So the first question you need to ask yourself is, what acid and base do this salt come from? For example, the first one, sodium chloride, come from sodium hydroxide, hydrogen chloride. Okay, so when they combine these two, hydroxy and hydrogen combine forms water, and therefore the rest is sodium chloride. Now, because hydrogen chloride is a strong acid, sodium hydroxide is a strong base. So the ions that come from strong acid, strong base, they are spectator ions. So sodium and chloride both are spectator ions. As long as they come from strong acid, strong base, the ions are spectator ions. They do not react with water or hydrolyze. Okay, so in this solution, there's no ion expect to hydrolyze. Okay, next one is sodium acetate. Okay, so here sodium comes from, again, sodium hydroxide, and acetate comes from acetic acid. Okay, and we know sodium hydroxide is a strong base, so sodium ion is a spectator ion. And the acetate ion is not a strong, does not come from strong acid. Instead, it's a weak acid. So weak acid, the ion will react with water, go back to the weak acid, and so it will hydrolyze. So C2H3O2 negative, and this ion will hydrolyze. So for example, it reacts with water, forms acetic acid, okay, C2H3O2, all right, because it takes one proton away from water, so what left is hydroxide. And this makes the solution basic. Okay, all right, so remember, strong ions from strong acid, strong base, they are spectator ion. From weak acid, weak base, they will hydrolyze back. Okay, so next let's do another one. Let's say copper nitrate. So copper comes from copper hydroxide. Okay, and is this a strong acid, strong base? No, it's weak, because again, how do you know? You go back to the list that I show you, strong acid, strong base, all right, and you need to memorize them. So this is not one of them, so it's a weak acid, weak base, and therefore this will hydrolyze. This ion will hydrolyze. And what about nitrate? Nitrate comes from nitric acid. Okay, nitric acid is a strong acid, so the ion is a spectator ion. It does not hydrolyze, does not react with water. Okay, and so this will react with water, forms copper hydroxide, go back to the weak base. At the same time, so you need two of them. At the same time, it generates hydrogen ion, make solution acidic. Okay, so all of this salt, you look at the cation. So these cations, they all come from base, and the anions come from acid. All right, so you look at the acid base and see if they are strong or weak. If they are strong, these ions will spectator ions. If they are weak, they will hydrolyze back to the weak acid, weak base. In order to work out the pre-lab questions, we need to go over the acid-base constants, ionization constants. And a weak acid ionizes in water. For example, nitrous acid ionizes to form hydrogen ion and nitrite ion. But hydrogen ion combined with water forms hydronium ion. So it's more appropriate to write nitrous acid with water forms hydrogen ion with nitride ion. Okay, and note that this reaction has two arrows, means it's the reaction also go back. So nitride ion combine with hydrogen ion give back the weak acid plus water. Now because it react with acid, so this is called base, and this is called conjugate base of the weak acid. So weak acid combined with water forms hydrogen ion and its conjugate base. The reaction has an equilibrium constant. The equilibrium constant is the product divided by reactants. So in this case, the product is hydrogen ion, and that's here, and the nitride ion divided by the weak acid is this one, and water. But water is a constant. Water concentration doesn't change. So if we ignore the water concentration, then this constant is called acid ionization constant, or simply acid constant, Ka. So the larger the Ka, the more hydrogen ion it produces, and therefore it's a stronger acid. Okay. Now we can define a concept called pKa. pK is negative log Ka. So the larger the Ka, the smaller the pK, because you have negative sign. So stronger acid give you a larger Ka but a smaller pKa. All right. Now, again, let's look at the conjugate base. The conjugate base not only react with hydrogen ion, if in water, it actually combines with water to give back the weak acid, because so in water you have HOH. This combined with one of the hydrogen, go back to the weak acid and leave hydroxide ion. So this serves as a base. Okay, react with hydrogen ion, so it's a base. All right, and this also have a equilibrium constant. So this equilibrium constant indicates how much hydrogen ion or hydroxide ion is formed. All right, if we again ignore water concentration, then this is called the base ionization constant, Kb, because it tells you how much hydroxide is formed. Okay, a stronger base, more Kb, higher or more hydroxide ion, and larger Kb. Okay, similarly, we can define pKb is a negative log Kb. So stronger base, larger Kb, smaller pKb. Now, if we combine Ka and Kb together, so Ka multiply by Kb. So this is a Ka, that's this one, and multiply by Kb is this one. All right, and you will see that the weak acid cancel each other, and the conjugate base also can cancel each other. So what we have is just the hydrogen ion multiplied by hydroxide. Hydrogen ion comes from hydrogen ion. So this is the product of hydrogen hydroxide, and that's the Kw. That's the water constant. Okay, water ionization constant, which is 10 to the minus 14. So here we have an important equation that is Ka multiplied by Kb give you a constant 10 to the minus 14. It's the water ionization constant. Okay, remember Ka tells you the strength of acid. The larger Ka means stronger acid. But the product is a constant. That means if you increase Ka, Kb must decrease. So a stronger acid, the conjugate base must be weak. On the other hand, if you have a weak acid, okay, weak acid means a smaller Ka, then Kb will be large. So the conjugate base will be a stronger base. Okay, if we take negative log on the left side, the right side also negative log. Negative log 10 to the minus 14 is 14. So the right side is 14. The left side is negative log Ka plus negative log Kb. Okay, the product log should be written as plus, okay, to add together. And this is pKa, and this is pKb. Okay, so now we have another important equation. pKa plus pKa, pKa plus pKb is 14. So if we know pKa, we can calculate the pKb. Or if we know pKb, we can calculate pKa. And these two equations are important that you will use for solving pre-lab questions. In this lab, you're going to use several indicators to estimate the pH range for some salt solutions. Now, indicators are chemicals that change color at different pH values. For example, methyl red, and this one appears as yellow color when pH is above 4.4, but change to red when pH is below 3.1. In between, it appears as orange color. Methyl red is yellow when pH above 6.0, but changes to red color when pH is below 4.8. Bromothiamine blue is blue color when pH is above 7.6, but yellow under 6.0. Phenol red is red when pH is above 8.0, but becomes yellow when pH is below 6.6. Phenolphthalein is red above 10.6 or 10.0, but colorless below 8.2. And alizarin yellow R is red when pH is above 12, but change to yellow when pH is below 10.1. So these two changes color at acidic condition, but this two changes color at basic condition. Okay, so these two is close to neutral solution when the color change. So, for example, if you have an unknown solution, you want to test the pH value or pH range, and you add, let's say, this one, bromothiamine blue, and the color becomes blue. So what does that tell you? It tells you the pH value for this solution is probably above 7.6, because the blue color is about 7.6. And then you add phenolphthalein, and you find out that the color is colorless, and that means the pH value is less than 8.2. Okay, so phenolphthalein is colorless when pH is below 8.2, and therefore the pH value of this unknown solution is lower than 8.2 and greater than 7.6. So this gives you a range. All right, so therefore we can reasonably determine the pH range of the salt solution by using these indicators and evaluate the results. So again, this is just estimate, so not very accurately determine exactly what pH value, but give a range. In this lab, you are going to test these samples using methyl orange, methyl red, bromothiamine blue, phenol red, phenolphthalein, alizarin yellow R. You need to write down the color, okay, of each indicator for these samples, and then from the color you need to estimate the pH range, and then from this estimate the pH value, you estimate the hydrogen ion. Remember, pH is negative log hydrogen ion. So if you know pH value, you can calculate hydrogen ion and then calculate hydroxide ion. Okay, remember hydrogen times hydroxide, all right, is 10 to the minus 14. All right, so you calculate each of these sample. The first two samples are both water. Okay, one is unboiled, one is boiled. So water, we know that in the air we have CO2, carbon dioxide, that can dissolve in water. So if water is unboiled, it must contain CO2, and CO2 in water forms carbonic acid. So it should be acidic, slightly acidic, if the water is unboiled because of the CO2. All right. Now, when you boil it, okay, the CO2 will evaporate. So eventually, you get a pure, almost pure water. So in other words, there's no CO2 in it. So it should be close to neutral after you boil it. All right. So you will see the difference between these two using these indicators. And then sodium chloride and sodium acetate. So all these you will measure the color change for all these indicators. In this lab, the TA will prepare a large amount of pre-boiled DI water for use. So first, you need to gather a test tube rack with six 6-inch test tubes. You need to label each test tube with an indicator shown below. Okay, and then you add unboiled DI water into each of these test tube. Okay, 5 milliliter unboiled DI water, and after that you add 3 drops of indicator. So first tube you add methyl orange as you labeled, and the second you add methyl red, okay, and third one bromo thymo blue. Okay, each time when you add indicator, you need to observe the color change and then record the results. So these are the results for unboiled DI water. Okay. After you finish testing the unboiled DI water, and now you need to test the boiled DI water. So first rinse the test tube with boiled DI water. So you need to clean them. And then again, you label each test tube with the indicators shown here. And now you add boiled DI water, 5 milliliter, into each of the test tube. Okay, and then you add indicators. So again, first add methyl orange and then methyl red as shown in this sequence. And then observe the color change, record the results. So this results is for boiled DI water. After you finish testing the boiled DI water, now you need to test the pH value for sodium chloride solution. But first you need to clean the test tube. So rinse the test tube with boiled DI water. Clean these test tubes, and then label each test tube with these indicators, the names of indicators. And now add 5 milliliter, 0.1 molarity of sodium chloride solution into each of these test tube. And then add 3 drops of indicators, first methyl orange and then methyl red as shown here. Observe color and write down the color. Okay, so this finish the test of sodium chloride, and then repeat these procedures for 0.1 molarity of sodium acetate, and the next will be copper nitrate. So ammonium chloride, zinc chloride, potassium aluminum sulfate. So test all of them according to the procedures shown above, and then estimate the pH according to the color change, and then calculate the hydrogen ion, hydroxide ion, and then calculate the Ka and the Kb. This is one of the tables you need to finish and turn in with your report. And here shows the list of salt, okay, that you are going to measure. And this asks you the net ionic equation for hydrolysis. So again, the first question you ask is what acid and base do this salt come from? So let's look at the first one. And so sodium comes from sodium hydroxide. Okay, this is a strong base, and because of strong base, sodium is a spectator ion. It does not hydrolyze. Okay, now the anion C2H3O2 that comes from a weak acid, and so HC2H3O2. Okay, and how do you know it's a weak acid? It's not in the list. All right, and so it's a weak acid. In fact, it's a acidic acid, and because come from weak acid, so the anion should hydrolyze back to this acid. So you write C2H3O2 negative. Okay, and why it is a negative? Because sodium is a positive, so it's a cation, and this should be an anion. So negative plus water go back to the weak acid HC2H3O2, and it takes one hydrogen away from water, so water now becomes hydroxide. All right, so in this reaction, this anion serves as a base. Okay, because it takes hydrogen away from water. It reacts with hydrogen, so it reacts with acid, and therefore it's a base. And this is called a conjugate acid. Okay, so base conjugate acid. All right, it generates hydroxide, and so this reaction should give you Kb. Kb is the basic base constant. This is in this reaction, this is a base. Okay, it gives you hydroxide. So Kb. All right, so Kb is the equilibrium of product divided by reactants. So product is the weak acid HC2H3O2 times hydroxide anion. Okay, so the product divided by reactants, here a reactant is the anion C2H3O2 minus. And what about water? Okay, you don't need to include water in this equation. If you do, that's called equilibrium constant. For Ka, Kb, you ignore water concentration, so that's Kb. Now, how do you calculate in this column? How do you calculate the Kb or Ka? Okay, so you need to use the pH value. So the pH value you already estimated in the previous tables. Okay, from the color change of this salt, you estimate pH value of this solution, and from there, and combined with this equation, you should be able to calculate Ka, Ka or Kb. We're going to show you how to do that in one of the pre-lab questions, okay, later. All right, so that's the first one. Now the second one is similar. Okay, so again, sodium is a strong base, carbonate comes from a weak acid. So you write similarly, so you should write carbonate. plus water forms carbonic acid, generate hydroxide, okay, and you write Kb because again it serve as a base, But note here you add water. Okay, let's write it. So here the acid should be H2CO3, okay, because the carbonate is 2 negative, so you need 2 of them, and you generate 2 hydroxide, 2 of them, all right, 2 water. Okay, so when you write Kb, the weak acid, okay, let me write it, and note here, negative hydroxide should be squared, because when in the equation, if your coefficient is 2, so here you have a 2, then you need to square it. Product should be squared, and then divide by CO3 2 minus. So again, from the color, you estimate pH, then you can calculate Kb, calculate Ka, all right? And so these two are similar, and then these three are similar. They come from weak base, strong acid. So for example, zinc chloride comes from zinc hydroxide and hydrogen chloride. So hydrogen chloride is a strong acid, so chloride does not hydrolyze. It's a spectator ion. But zinc hydroxide is a weak base. It's not in the list of the strong base. So zinc will hydrolyze back to this weak base. So you write zinc 2 plus water forms zinc hydroxide, okay, plus proton. Okay, when water lose hydroxide to form zinc hydroxide, it forms hydrogen ion, and because it takes 2 hydroxide, so you need 2 water, and then you generate 2 proton. Okay, so this reaction, zinc ion serves as a acid, so it's an acid. Okay, and because it reacts with hydroxide, it forms zinc hydroxide and generate proton. So when you write equilibrium, this is called Ka, acid constant. And again, you write the product zinc hydroxide and proton concentration, but square. Okay, you have 2 here, so you need to square it and then divide by zinc cation. Do not include water. All right, otherwise it's just equilibrium constant. Here is a Ka. Okay, Ka is similar to equilibrium constant, but not the same. You don't include water concentration. And then from pH value, you calculate the Ka, you calculate the Kb. All right, you do the same for copper nitrate, ammonium chloride. Okay, because copper hydroxide is a weak base, ammonium is a weak base, but nitrate comes from nitric acid, so nitrate should be a spectator ion, doesn't hydrolyze. Similarly, chloride does not hydrolyze. All right, so these two are similar. All right, now the last one, sulfate comes from sulfuric acid, so sulfate shouldn't hydrolyze. It's a strong acid. Potassium comes from potassium hydroxide. That's a strong base, so potassium shouldn't hydrolyze. But aluminum does. Aluminum comes from aluminum hydroxide. Okay, so that's a weak base. It's not in our list of the strong base, and so you should write aluminum 3 plus. Okay, plus water, hydrolyze back to aluminum hydroxide. All right, plus hydrogen. Okay, so you need 3 hydroxide, so you need 3 water, you need 3 hydrogen ion, and in this reaction, again, aluminum serves as an acid because it takes hydroxide away from water. And so it's acid, so you write the Ka. All right, so aluminum hydroxide times hydrogen cation third power. Okay, again, because this has a 3 divided by aluminum ion concentration and do not include water. And then you calculate the Ka from the pH that you estimated, and then calculate Kb. You need to include SDS for all the chemicals in your report. Here are the list of the indicators and then the salts, okay, you're going to measure. Prelab questions. Question number 1. Define Bronsted-Lowry acids and bases. Bronsted acids are proton donors. One example is HCl. This will donate a hydrogen ion or proton. Bronsted bases are proton acceptors. Sodium hydroxide will react with hydrogen, so it will form water. So hydroxide, hydrogen form water plus sodium ion, and therefore this is a Bronsted base. Ammonia also react with hydrogen. Okay, it's a proton acceptor. So this is also a Bronsted base. Okay, question number 2. Which of the following ions will react with water in a hydrolysis reaction? So you should look for the ions come from weak acid or weak base. First one, sodium ion come from sodium hydroxide, which is a strong base. So this will not hydrolyze. Same thing is for second one, calcium. But the copper ion, this comes from a weak base. Therefore, this will hydrolyze. Zinc ion comes from weak base. This will hydrolyze. Fluoride comes from hydrogen fluoride. Even though hydrogen bromide, hydrogen chloride, these are strong acid, but hydrogen fluoride is not a strong acid, and therefore fluoride will hydrolyze. Sulfite, and this is comes from a weak acid. Even though sulfuric acid, SO4, that sulfuric acid is a strong acid, but sulfurous acid, SO3, that's a weak acid, and therefore this will hydrolyze. And bromide comes from hydrogen bromide, so it won't. Question number 3. For those ions in question 2 that undergo hydrolysis, write net ionic equation. So for copper ion, it reacts with water, so it will go back to the weak base, copper hydroxide. So after hydroxide taken away from water, you have hydrogen ion. Okay, so if we write as hydrogen ion instead of hydrogen ion, then you need to add 2 water, because 1 water give you 2 hydroxide. Actually, you need 3 of them, because 2 water forms 2 hydroxide and 2 hydrogen ion, which combine with water. So here you need to times 2, and actually you need 4. Okay, so 4 water. And next one, zinc plus water. So go back to weak base, and again it takes 2 hydroxide, so you need 2 water, but because we forms hydrogen ion instead of hydrogen ion, so you need 2 more water. So again this is 4, okay, and this is 2. Okay, next one, fluoride ion go back to the weak acid, So you take a hydrogen or hydrogen away from water, so you have hydroxide left. And next one, sulfurous, okay, sulfite. Okay, this add water hydrolyzed back to the weak acid and leave a hydroxide. Question number 4. The Ka or acid constant for hydrogen cyanide is given. What is Kb or base constant for cyanide ion? So we learned that acid constant and base constant product is Kw, which is called water autoionization constant. So if Ka is given, then Kb can be calculated by Kw divided by Ka. So in this case, it's 10 to the minus 14 Kw divided by Ka. And the answer is 2.04 times 10 to the minus 5. Okay, so the point of this question is you can calculate the Kb if you know Ka, or if you know Kb, you can calculate the Ka. Next question, what are the conjugate base and the conjugate acid for dihydrogen phosphate ion? So this one comes from a neutral acid which is called sulfuric acid. So that's H3PO4. Note that you have a negative charge. So if you combine one positive proton, that's a neutral acid. Okay, this is called a sulfuric acid. Sulfuric acid is a polyprotic acid because it has 3 protons. So it can donate 1 proton, okay, and that gives you dihydrogen phosphate ion. And this dihydrogen phosphate ion still have 2 hydrogens, so you can donate another hydrogen, give you hydrogen phosphate ion, but now you have 2 negative. Okay, and the question is about this dihydrogen phosphate, and you can see this can participate in several reactions. One is this step. Okay, in this reaction, sulfuric acid is acid because it donates a hydrogen, and this will be the conjugate base. Okay, so if we donate a proton, that's acid, and the product is a conjugate base. Now the conjugate base also hydrolyzes back to the original acid by adding water, and then this is the base, and this will be the conjugate acid. So the reaction is dihydrogen phosphate plus water go back to the phosphoric acid and with a hydroxide ion. And so in this case, we call this base, and the product is a conjugate acid. Now the dihydrogen phosphate can also participate in the second reaction. In this case, this ion donates a hydrogen or proton, so this is acid. Okay, because it donates a proton to form the product, and this is acid, and this must be the conjugate base. Okay, so here we write the dihydrogen phosphate donate a hydrogen, or you can write add water forms hydronium ion. Okay, now sometimes simplified written is you just donate a proton, but more accurately, it add water forms hydronium ion and gives you a hydrogen phosphate ion. Oh, sorry, this is hydrogen phosphate ion. Question number 6. From what acid and what base were the following salts made? First one, calcium sulfate. The cation calcium comes from base calcium hydroxide, and the sulfate comes from acid. So one is calcium hydroxide, another is sulfuric acid. Next one, again, the cation comes from base. In this case, ammonium cation come from ammonia base. So this is a weak base, ammonia. This is ammonium cation. And the anion come from acid, hydrobromic acid. Okay. Next one, again, cation barium come from barium hydroxide base, and the chloride come from hydrogen chloride or hydrochloric acid. Okay, next one, define the term salt. All right, so we know that acid base combine forms water and salt. Salt comes from acid base reaction. The cation come from base, anion come from acid. So we can say salt is a chemical compound consisting of assembly of cations and anions. Cations come from base, anions come from acid. Question number 8. Tell whether 0.1 molarity solutions of the following salts would be acidic, neutral, or basic. To answer this question, you should first ask, what acid and base do this salt come from? If both are from strong acid, strong base, both are strong, then it's neutral. So the first one, barium ion come from barium hydroxide. Remember, barium is group 2. So both group 1 and group 2 cations, they are come from strong base. So for example, lithium hydroxide is a strong base. Barium hydroxide is a strong base. Chloride comes from hydrochloric acid, so both are strong, and therefore this is neutral. Okay, so both ions are spectator ion, they don't hydrolyze. Next one, sulfate. Okay, this comes from sulfuric acid, so it's strong. But copper comes from copper hydroxide, that's a weak base. And remember, strong one wins. So this is weak copper base, this is weak, but this is strong, acid is strong. And therefore the solution should be acidic, okay, because you have a strong acid. Now the real reason for this, you should write hydrolysis reaction. The copper ion, which comes from weak base, hydrolyze back to the weak base. Okay, by taking hydroxy away, the water becomes proton. Okay, so in this case we can write hydrogen ion. All right, so you need to 4 of them, and this is 2. And so the real reason is the copper ion hydrolyze back to the weak base, give you hydrogen ion or proton, and that make it acidic. Okay, that's acidic. But simply we can just think strong one wins. So in this case, weak base, strong acid, so acid wins. Next one, ammonium comes from weak. Again, this is a weak base, and the sulfuric acid is strong. So again, strong wins, so that's acidic. Okay, next one, this one, zinc is a weak base, chloride is strong acid, so same thing, that's acidic. So next one, sodium comes from a strong base, sodium hydroxide, but the cyanide comes from a weak acid, hydrogen cyanide, and therefore in this case sodium hydroxide wins, so that's a basic. But remember, the real reason is actually hydrolysis, cyanide plus water, hydrolyze back to the weak acid. But when you take proton away from water, you have hydroxide. That makes solution basic. Okay, next question. If the pH value of a solution is 9, so you know pH value. The question is what are the hydrogen and hydroxide concentration? And to do that, we know the definition of pH is negative log hydrogen ion, okay, which is 9. So to do that, you can use your calculator. One way to do it, you move negative sign to the right side, so you have log hydrogen ion equals -9, and then hydrogen ion concentration should be anti-log -9. Okay, so that will give you 10 to the -9 power. So with this hydrogen concentration, we can calculate hydroxide because the product is 10 to the -14. So hydroxide should be 10 to the -9 divided by so 10 to the -14. That's the water constant divided by 10 to the -9. Give you this one. Question number 10. The pH value of a 0.1 molarity MCl was found to be 4.6. M is an unknown cation. So if you look at the list of the salts that you will do in this experiment, some of them resembles this salt. For example, ammonium chloride. Okay, so in this salt, ammonium is cation M+, and the chlorine is the anion. All right. Now we already know that this salt should be acidic. Okay, because this comes from strong acid, and this is weak base. Strong acid wins. Remember, so that's why it's acidic. In fact, the real reason is because ammonium ion hydrolyze back to the weak base, and so this is a hydrolysis reaction, and here M+ is the NH4+. That's the cation go back to the weak base and generate hydrogen ion. And because it generates hydrogen ion, so the solution is acidic. And therefore, this equation gives you Ka. Okay, it's acid constant. Okay, because it react with hydroxide from water, give you more acid concentration. So it's a Ka. So the Ka is the product divided by reactants. In this case, is the ammonium hydroxide and hydrogen ion divided by ammonium cation concentrations. All right, and if we know the pH value, how do you know the pH value? You look at the color of the solution by looking at the when you add the indicators. So you estimate the pH value, and from pH value you calculate the hydrogen concentration. Okay, and so this is estimated, and then from this reaction equation you can also calculate the ammonium hydroxide product and the reactants, how much left, and you can calculate the Ka. Okay, we'll show you in a minute how we do it. So with Ka, okay, then we can calculate the Kb. So what is Kb? Kb is not this equation. Instead, is this base, weak base, forms cation with hydroxide, and the equilibrium for this one is Kb. Okay, but we already calculated Ka. Now Kb product Ka-Kb is Kw. So first you calculate the Ka, and then you calculate the Kb. And this procedure applies for all the salts, including ammonium chloride and zinc chloride and copper nitrate. Okay, so all these salt involves cations that comes from weak base. They all hydrolyze back, and the reaction is Ka. And from pH you calculate the Ka first, and then you calculate the Kb. Okay, so now let's see how do you calculate the Ka. So first you write the hydrolysis reaction. The cation go back to the base and generate hydrogen ion. Initially, we add 0.1 molarity of the salt, and that give you 0.1 molarity cation. Initially, you have no product MOH, and usually you should have no hydrogen ion, but we already know water actually auto-ionize to give you 10 to the minus 7 hydrogen ion, hydroxide ion. So hydrogen ion is hydrogen ion. Both are 10 to the minus 7. So this is a very small number, and it shouldn't affect reaction, but we can write here. All right. Now you don't have to write it because it's so small. Now that's the initial concentration before the reaction. So how much changed after reaction? So after reaction, we know hydrogen ion becomes this one. Initially, you almost had 0, only 10 to the minus 7 due to the auto-ionization of water. But now, after reaction, the pH value becomes 4.6. So hydrogen ion is 2.5 times 10 to the minus 5. So how much change is the product, okay, minus initial? That's how much change. But initial is very small compared to 2.5 times 10 to the minus 5. And so you can approximate just 2.5 times 10 to the minus 5. And so initial, as we show, we can just write as 0. And this is the final product. That's how much change. So this is how much generated, okay? And therefore, this is the same. You generate the same amount, hydrogen ion and MOH, same amount. And the reactants reacted is also the same. So because of the stoichiometry, you see the coefficient 1, 1, 1. Whenever we generate this amount of hydrogen ion, you generate also this amount of MOH, and you reduce. Okay, negative sign means you reduce this amount of the cation. So at equilibrium, you should use initial plus this change for the product. So same thing here, all right, the product. But the reactants, you should use initial minus this one because you reduce this amount. Okay, so that's the equilibrium. And therefore, we go back to the Ka. Okay, so this equation, again, remember this equation, equilibrium is related to the Ka, the product divided by reactants. So here at equilibrium, MOH, okay, for example, ammonium chloride is this one, and that's this hydrogen, this one, and the hydrogen ion is here, and the cation left is this one. And therefore, we calculate Ka to be 6.28 times 10 to the minus 9. And then, how do you calculate the Kb? Well, Kb is Kw divided by Ka. And that gives you 1.59 times 10 to the minus 6. So this procedure to calculate Ka and Kb applies again to all the salt, including ammonium chloride, all right, zinc chloride, copper nitrate. So all the salts that includes a weak base, a cation comes from weak base, and a strong acid anion. Okay, so you first find the pH value, calculate, find the pH value, find the hydrogen ion concentration. So a hydrogen ion concentration, and that's the product change. And so from there, you know the change for the cation, for the MOH, the weak base, and then the equilibrium is the initial concentration minus the change for the reactants, and plus the change for the product. And then you calculate Ka first, and then you calculate Kb. Okay? For other salts, the procedure is slightly different. In the last slide, we showed how to calculate Ka, Kb for the salt that contains a cation from weak base and anion from strong acid, such as ammonium chloride. So the solution should be acidic because the cation hydrolyzes back to the weak base, generate hydrogen ion, and the equilibrium constant is related to Ka. So you write Ka. And from pH value, you calculate the hydrogen ion concentration. And you list the table from initial concentration and the change, you calculate the equilibrium concentration of the weak base and how much cation left. And therefore, you first can calculate the Ka, and then you calculate the Kb. Okay? And I want to mention two things here. One is I use ammonium chloride as an example in the last slide. Now, in your lab report, when you calculate ammonium chloride Ka, Kb, you should not use 4.6. Instead, you should use the value you estimated from your experiment. The color change, you estimate the pH value, all right? And then you calculate hydrogen ion concentration, and then calculate the Ka, Kb for ammonium chloride. For other salt, okay, another thing I want to mention is, for example, zinc chloride. If you write hydrolysis reaction, zinc is 2+, and it forms zinc hydroxide 2 hydroxide, and therefore here hydrogen ion should be 2. Okay, and so you see the stoichiometry here, the coefficient is 2, and therefore when you write Ka, this should be 2. Okay, so the hydrogen concentration should be raised to the second power in Ka. All right, so the equation, equilibrium reaction, if coefficient is not 1, then equilibrium constant you should raise to the power of the number, and that's the second thing I want to mention. So next question is, how do you calculate a salt with a strong base with weak acid, for example sodium acetate? Okay, so this comes from a strong base, and this is weak acid, so the solution should be basic. Okay, and so we know the real reason is this anion hydrolyzes back to the acid, generate hydroxide. Now for simplicity, I use A to represent this anion, so this can be written as NaA. Okay, A represents the acetate anion, and so the hydrolysis reaction is A minus plus water goes back to the weak acid plus hydroxide. Okay, and that makes solution basic. And this equation is related to Kb. So it's the weak acid, hydroxide, and anion. Okay, so you write Kb for this hydrolysis reaction, and then you go from pH value. Okay, pH value is estimated from the color, and then calculate hydrogen ion concentration. Okay, because pH is defined as negative log of hydrogen concentration. So from pH you can calculate hydrogen ion, but Kb include OH, not hydrogen ion. So you need to calculate hydroxide concentration. Remember, the product is 10 to the minus 14. So from hydrogen ion, you calculate hydroxide. And then you write the same table as I shown in the last slide. So initially, how much salt you have, for example, 0.1 molarity for the anion, and for the product 0 and 0. Okay, in the last slide I wrote here 10 to the minus 7, but I showed that this is very small compared to the change, so you can write as 0 here. How much change? We already know that when the reaction becomes equilibrium, the hydrogen ion can be calculated. So let me write as question mark that estimated from pH value. So here should be question mark that you estimated. And due to the stoichiometry, the weak acid should also be the same concentration, and the anion left or change is negative, the change. Okay, so this is positive, this is positive, this is negative. So what's the concentration at equilibrium? Is the initial minus the change. Here the same. So plug in all these to Kb, so you can calculate Kb, and then from there you calculate Ka. All right, so you note the difference for ammonium chloride salt. For this salt with weak base, or cation from weak base, anion from strong acid, you write Ka. Okay, hydrolysis give you hydrogen ion, you Ka, and then pH value calculate hydrogen ion equilibrium concentration, you calculate Ka and then Kb. But for base sodium acetate, okay, you calculate Kb first. Okay, even though you know the pH value, you can calculate the hydrogen ion, but you still need to calculate hydroxide ion, and then you calculate the Kb. From Kb, you calculate the Ka. Okay, and this also applies to sodium carbonate. Okay, and again, remember, if equation have coefficient not 1, then you should raise to the power in Kb or Ka, raise the power to the number.